Oh shoot, hello? All right, does it work now?
Yes.
Oh my God, okay, sorry, my bad. All right, let me go back, I guess. Sorry about that for the audio. But yeah, so this week we'll be continuing some combination problems. So we're gonna spend, hopefully this is the last week we'll be learning new things about this, since this is a really important concept for math, especially later on when we do competitions like the AMC 8, AMC 12, or AMC 10, and so on. So we're gonna first go over some review, the factorials, permutations, and combinations. So we learned all of these last week. And after that, we'll go over some new concepts. So symmetric counting, counting with restrictions, and we can put it together in sort of like some puzzles with grid problems. Okay, so quick review. Let's go over the factorials. Let me explain this again since I was muted last time. So we write it as a number plus the exclamation mark after it. So what this means is just its number times itself minus 1 times itself minus 2. So it's just multiplying the number by itself, and it's just slowly counting down until it reaches 1. So for example, if it was 4 factorial, which is written 4 exclamation mark here, you see it's 4 times 3 times 2 times 1. So if it was 5 factorial, it'd be 5 times 4 times 3 times 2 times 1. And this is the same for like all numbers. So this is used for some pretty basic permutation problems. So a quick review, this problem is Loy has 10 books on a shelf. So how many ways are there to arrange his books on a shelf? So we can use the factorials to do this. Does anyone have any idea how to tackle this problem? Yeah, Kimi, go ahead.
I think if he has 10 books on a shelf, probably 10 factorial.
Yes, 10 factorial, that's right. So we do 10 factorial because of the choices for the books, right? So let me go draw this out for you guys. Let me find a new slide here. So let's say we have the 10 books, right? We'd want to put it on a shelf. So when we are selecting the first book to put on the shelf, we have 10 choices, right? We have 10 books to choose from. So that's why we have the first number is 10 here. But after you put the first book on the shelf, we only have 9 books left to choose from, right? When we finish drawing all these books here. So our first choice for the books, right? We have 10 books to choose from, so that's 10. The second time we choose, since we already used one of them, we only have 9 books to choose from. So the second one would be times 9. Cross that out. We have already used 2 of them. Now you have 8. And this continues so on and so forth. So we go times 9, times 8, times 7, and so on. So that's written as 10 factorials. The answer here would be 10 factorial. So does that make sense, everyone? Yeah, all right. So permutations. So these are a little bit more difficult. And the difference here is you can see it's pretty similar when we're looking at this equation here. It's pretty similar to the permutations. Or not the factorials. We still have the number factorial on top. But on the bottom, we have the number we're choosing here, which is n minus r. So you can write this in a few different ways and do p and r, or this method of writing it. The notation is slightly different sometimes, so we're not going to worry about that too much. So the problem we're going to use this for is quick review here. There are 10 students in Kimi's class. The teacher wants to choose 3 students to be president, vice president, and treasurer. So how many ways are there to choose the 3 officers if each student can only have 1 position? So this problem is different from the earlier problem, right, we had with the books. So how is it different? Anyone have any idea why we'd use the permutation here instead of the just simple factorials? You guys can use the chat too. You can unmute or use the chat. So this problem is different because we're still choosing from 10 things, right? We have 10 students in this class that we're choosing from, but we're only choosing 3 out of the 10, not all 10 students. So instead of looking at this equation, let's first look at this logically. So how can we solve for this just using our, simple logic here? So when we're choosing let's say we go president, vice president, treasurer in that order. So when we're choosing president, how many choices do we have out of the 10 students? Anyone have any idea? Yeah, 10 people, right? We haven't chosen anyone. So after we choose the first person, which is 10, we're choosing the second person, we have 9 people left, right? And then we wouldn't continue down. We wouldn't write this as 10 factorial because we wrote this as 10 factorial. This is assuming that we're going to choose every single one of them, but we're only trying to choose 3 out of the 10. So instead of writing 10 factorial, it'd only be 10 times 9 times 8. So does that make sense? We have 10 for the first choice here. After you chose, we have 9 and we have 8. So this is our president, our vice president, and our treasurer. So going back to this, the reason that equation here is it's just we're dividing by the overcounting. If we just do 10 factorial here, we're overcounting the number of students here. So that's why we divide by n minus r. So if we're doing that last problem here, n minus r would be 10 minus 3, which is 7 factorial. And that would divide here, leaving us only 10 times 9 times 8. So does that make sense, everyone? If you have any questions, please ask. So we make sure you guys understand this. All right, Joyce has got it. Everyone else all good? All right, Kimi's giving me a thumbs up. All right, and also if I go ahead and you guys still have a question later on, feel free to ask in the chat or you can unmute. Alrighty, so the last thing we went over last week, which is combinations. And again, we don't have to think about this scary formula here. This make it look pretty intimidating, but we can solve this all using just basic logic and then apply the little equation / formula thing later. So let's look at this problem first. There are 10 people in Hanson's class. The teacher wants to choose 3 people to form a volunteer committee. So how many ways are there to choose the committee? So how is this different from the previous problem? Let's think about that again. Anyone have any ideas? Okay, so this is different because we're forming a volunteer committee. So here, the 3 people that the teacher is choosing are all the same. So we don't have to differentiate between a president, a vice president, and then a treasurer, right? So that's where this equation comes in here. As you can see, we've added another r factorial. So this r factorial here is the number of people that we're choosing. So this r factorial, this extra one up here, what this does is it gets rid of the overcounting. So if we were to tackle this problem, like we did earlier, right, just 10 times 9 times 8 because of the 3 different choices, we would find that we overcount because what we're doing here is assuming that these 3 positions are different, right? So this is correct when there's a president, a vice president, and then the treasurer. But when everyone is the same, when you're forming a committee, this is overcounting. So that's all you have to divide by an additional r factorial. So in this case, we would divide by additional 3 factorial because we have 3 factorial different ways of arranging them. If you arrange these 3 people in the committee, we'd have 3 factorial ways of arranging them. Again, we have 3 choices times 2 and then times 1. So that's how many times we're overcounting, which is why we have to divide by this additional one here. So for tackling this problem, how would we do it? Anyone have any idea? Remember, you don't have to look at this equation up here. Just think about it logically. Neo, Loy, oh, Kimi. Yeah, go ahead.
maybe it's 10 people, 10 factorial,
Mhm.
and then minus, divided by 10 factorial divided by 3 factorial, and then like the equation, like right here, this one.
Yeah.
So it's gonna be 10 minus 3,
Mhm.
which is 7.
All right, so now that we've used the equation, we understand how the equation works, right? So now why did we choose all these numbers? So the 10 factorial here, this is because we have 10 people, right? So we have 10 factorial ways to arrange these 10 people. Again, 10 people and then times 9 people to choose from, times 8 people, and so on. Right? So this is number of ways to arrange the people. So now why do we have these two numbers down here? So the 7 factorial here, this is actually because we're only choosing 3 people out of the 10. So the additional people don't matter. So to better help you guys understand this here, I'm gonna draw out the math for this. Okay, so when we're doing 10 factorial, it's 10 times 9, 8 times 7 times 6, and so on. Right, that's 10 factorial. And on the bottom, we wrote 3 factorial. We're gonna ignore that for now, times 7 factorial. So 7 factorial is this. So as I'm writing this out, do you guys notice any similarities between the top and the bottom? You guys notice anything here at the top?
I noticed one.
Yeah.
10 minus 7 equals 3, so that's where you got the factorial, 3 factorial.
Yeah, but just looking at this equation here, remember, we're trying to understand why you have to divide by 7 factorial. So what you guys will notice is that you see here, this bit of the equation, let me use a different color. Let's go with yellow. This bit of the equation here is the same as this, right? It's all 7 times 6 times 5 times 4 times 3 times 2 times 1. So once we cross cancel these, because again, if you have the top and the bottom here and they're multiplying by the same things, we can cross cancel this. So all this actually goes away. So what does that leave us with? 10 times 9 times 8. And again, we have this because we're trying to choose 3 people out of the 10. Right, so we have 10 choices for the first person, 9 choices for the second person, and 8 choices for the third person. And we don't need to multiply any of that. If we multiply by any of these, that's assuming that we're choosing more people. Each one of these multiplications is another choice, but we're only looking for 3 people. So that's why I have to divide at the bottom here. But again, you don't have to use this equation every time. If you're just thinking about it, we have 10 people, we're choosing 3. And we care about the order, you would just do 10 times 9 times 8. And then that 3 factorial earlier, this kicks in here because we're over counting. Remember, when we're tackling this problem here, in Kimi's class, there is a president, a vice president, and a treasurer. But in Hansen's class, these 3 people are part of a committee, so they're all the same. So you don't care about which order we choose these 3 people. The 10 times 9 times 8 is assuming that we care about the order, but when we don't care about the order, you have to divide by how many times we chose this. So the 3 factorial is the number of ways to arrange 3 people, right? If you have 3 people and we're arranging them, or 3 books and we're arranging them on a shelf, we have 3 choices for the first book, times 2 choices for the second book, times 1 choice for the third book. So that's why we divide by the 3 factorial here. So what we're left with here, let me draw this somewhere else again. We're left with 10 times 9 times 8 divided by 3 times 2 times 1. The top here is the choices for the 3 people, right? 10 choices, 9 choices, 8 choices. And the bottom is dividing by how many times you overcounted. The 3 times 2 times 1 is the number of ways we can arrange these 3 people. That's why we're dividing the bottom. So does that make sense, everyone? Again, don't be scared by that big equation or the big formula. All right, anyone have any questions here? Guys, don't be afraid to mute and ask questions if you ever have anything you're not fully understanding. That's the goal of this math circle. Okay, cool. We've gone through combinations, permutations, and factorials. So now let's move on to some new concepts. So now we're going to talk about counting with symmetries. So here's where it gets a little bit more difficult. Again, we're going to try to use just logic to solve these instead of depending on a formula. So there are 5 people sitting in a circle. How many ways are there for them to sit down? So this is an interesting problem, right? Let me draw out the problem so you can all visualize this. We're gonna have 5 spots. There's 1, there's 2, there's 3, 4, and 5. So there are 5 spots in the circle, right? So how many ways are there for 5 people to sit down? Anyone have an idea of how to tackle this problem or any observations about the problem? Because this is pretty different than anything we've done earlier. Again, it's building on the same basic concepts. You have one person here, another person here. Five factorial. Now that's a pretty good first guess, right? We have 5 spots. We're trying to arrange the 5 people. But the problem with this is that if we draw these 5 people here, actually, I'm going to go to a different slide here real quick to help you guys visualize this problem. So the problem with just drawing or just leaving room for 5 factorial is that we're not counting the times we overcount. So these people here could be number 1 could sit here. Oh, number 1, number 2 could sit here. Number 3 could sit here. Number 4 could sit here. Number 5 could sit here. But it's the same order if we just rotate all of them, right? So what I mean by that is this here is essentially the same as having these people sit something like this. I'll draw it again. Over here in the corner, a little bit smaller. This is the same as having 5 sit here, 1 sit here, 2 sit here, 3 sit over here, and 4 sit over here. So the only thing I did between this one, the big one here in the middle, and the one in the corner is I rotated them. Right? Everyone shifted clockwise 1 position. So even though this looks different in relation to each other, the people are still the same. So 1 is still sitting between 5 and 2. 3 is still sitting between 2 and 4, right? So by doing 5 factorial, we're not accounting for this. So does that make sense? Here's where it starts to get a little interesting. Everyone got this? Because we're going to be building on this to solve the problem. This right here is the most important part. The math is not as important as long as you understand the sort of logic behind it. All right, Kiwi's got it. Anyone else? All good? All right, so the way we can avoid this overcounting is by dividing by the number of seats we have, right? So if you think about it, we can rotate these people 5 different ways. We have this normal thing here where 1 is at the top, and we can rotate them differently. So 5 can be at the top. Let's say the top is where this arrow is. I'll draw it in between. Let's say the top is where the green arrow is. Okay, 1 could be sitting here, or 5, or 4, or 3, or 2. Right? As long as we rotate everyone, it's all the same people sitting in the same sort of, like they're all sitting the same, like next to each other. They're all sitting next to the same people. So we have to divide by 5, right? Because there's 5 spots, there's 5 different rotations. So Kimi, your 5 factorial is right, but we also have to divide by an additional 5 after that. So the answer to this problem, let's go to the next slide, is 5 factorial divided by 5. And this equals 4 factorial. All right, cool. So does everyone make sense? Does that make sense for everyone? Again, here's another visualization of this problem. As you can see, they're just rotated differently, right? Oh, didn't mean to click that. All of these here are the same. These are all these different colors are next to the same different colors every time. Does everyone understand that? So let's try a quick problem here. Pretty much the same concept. I'll draw it on here. So let's say we have this time instead of 5, let's say we have 7 people. So you have 7 people sitting in a circle. So how many different ways can we arrange these people? Anyone have a guess? This problem? This is pretty much this is exactly the same concept as we went over earlier. So think about the logic or how you would solve this. All right, 6 factorial. Yeah, 6 factorial is right. So how did you come to that conclusion? Seven factorial divided by 7 or 7 factorial? So it should be 7 factorial divided by 7, right? Because 7 factorial, the top part here, that's how many different ways we can arrange the 7 people. And then we're dividing by 7 on the bottom because we have 7 different ways to rotate these people since they're in a circle. And every time we rotate them, they're still sitting next to the same people. So that's actually overcounting. So to put it in a different way, the 7 factorial is assigning people to seats. But we care about who's sitting next to who, not which seat they're sitting in. Does that make sense? Alrighty, so let's move on. We're gonna do some. Oh, so that was the problem here. So again, here's another visualization of that. See, they're rotated here, but they're all next to the same people. So that's again overcounting. So we don't want to count this one here. Okay, so now let's work on some different problems. So this is counting with restrictions. So this is different again. So let's read the problem. Eric, Finn, Armin, Jay, and Luke are sitting in a row of chairs. Eric and Finn really like each other, so they must sit next to each other. How many ways are there to seat the 5 people in a row? So Eric and Finn here are best friends, so they have to sit next to each other. And again, they're in a row of chairs. So this is not like the circular, they're not sitting in a circle. So anyone have an idea of how you can tackle this or the problems that you might encounter when solving it just like a normal counting problem? Yeah, Kimi, go ahead.
I'm just guessing, but it could be like the easiest thing you would think is 5 factorial minus divided by 5. But then we wouldn't like fill the need of Eric and Finn together. So I'm thinking it's 5 factorial divided by 4.
It's not quite the answer, but your thought process is really good. I like how you tackle that problem. So the way we can make sure, so let's think about this. We only need to focus on making sure that they sit next to each other at all times. So when we're counting them, how can we count them? Like, is there something we can do to make sure that we always count them as sitting together? Anyone have an idea for this? Loy, Neo, Joyce, Elizabeth, you guys got any ideas? Nope. All right, it's okay. So let's think about this. If we want to make sure they're always sitting next to each other, we can just pretend they're the same person. We can count them as one person, right? Does that make sense, guys?
Does that mean 4 factorial minus 3?
We don't need to minus, we don't need to subtract anything from this problem.
Oh, I forgot.
Yeah, because
So
this is
4 factorial, it's just 4 factorial.
Almost. So 4 factorial is the beginning of this. So let's think about this. This is pretty much like the bookshelf problem, right? We're just doing factorials. You don't need to minus or divide by anything. But we do encounter a new problem with our solution. If we put here, let's say these two people are blue and red, right? If we always put them next to each other, we count them as one person, we group them together. We're missing some possible combinations, right? So what combinations are we missing? We're missing the ones where it's first, let's say it's first Finn,
Blue.
then Eric, or it's first Eric, then Finn. So we're missing the time when it's red, then blue versus blue and then red. I'm going to draw the other people here. We're just going to put them gray because we don't really need to worry about them right now. Right? So these two are different, right? These two drawings here, the one I have on top and the one I have on the bottom, they're clearly different because one is red first, then blue. This bottom one is blue first and then red. But when we combine these people, we're counting them as one person. So we actually miss these combinations. So to add that back, we have to multiply our 4 factorial here by the number of ways you can arrange these two people. So how many ways can we arrange these two people? Yeah, 2 ways, right? Because we can either go red first then blue or blue first then red. If we're thinking about it mathematically, 2 choices and then 1 choice. So we have to multiply that by 2 or 2 factorial. So does that make sense, guys? That's how you solve this problem. Any questions for this?
Does that mean it's 6 factorial?
Not quite. So for writing this math out here, it's not quite 6 factorial. So 4 factorial times 2 factorial is the equivalent of this. Let me write it out. Yes, you can see this is not 6 factorial, not quite. So the first bit here, this is the 4 factorial, and we're multiplying by the 2 factorial. All right, let's move on to a different problem. So same concept. So this time we have some different people. Kimi, Olivia, Lois, Joy, Jack, Walter, and Aaron are sitting in a row. So we have how many people? 1, 2, 3, 4, 5, 6, 7 people are sitting in a row. So Joyce must sit next to Jack, while Aaron must sit next to Walter. So how many ways are there to seat 7 people? Let's start by visualizing the problem again. I'm going to draw it out here. So do you guys have any ideas for how to solve this? This is pretty similar to what we went over earlier with the first example of this restriction. So what people, Joyce, okay, so there's 2 groups. So I'm gonna color these people here. It's gonna be blue and red must be together. And then we'll say green and yellow have to be together.
Why?
Let's just say they're best friends here and they want to be in line together.
Okay.
Yeah, so you want to have any ideas for how to do this?
I think I know. 7 factorial minus plus times 2 factorial. No, 7 factorial times 4 factorial.
So the first bit's right, but why'd you choose a 4 factorial?
Because since the first time there were 2 ways of doing it, now there's 4. Oh.
Your 4 factorial is close, right? So if it was 4 people that had to be together, then we would multiply by 4 factorial. Remember, the people have to be grouped. There's only 2 people and 2 people.
So it's times 2 factorial times 2 factorial.
Yeah. Oh yeah. Also, it's not 7 factorial here because remember, we're grouping these as 1. So
So it's 5 factorial.
yeah. So yeah, I was wrong about the 7 factorial. It's actually 5 factorial here. Oh, it's not a very good 5. Yes, does it make sense, everyone? We're grouping these two people. We're going to count them as one person because they always have to be together. And these other people are counted normally. So that leaves us with 1, 2, 3, 4, 5 people. We're putting them in line. We care about order. That's just 5 factorial.
I'm probably the one right here.
Yes, everyone else is like over here. You guys can fill in here. Yeah, so we're multiplying by the 2 factorial times the 2 factorial. So again, these two people, they can be arranged in 2 factorial ways. And then these two people can be arranged in 2 factorial ways. So that's our final answer. So does that make sense, everyone? Remember, if you have any questions, feel free to ask them. This is this way of thinking, not necessarily memorizing this type of problem, but this way of tackling the problem is going to be important.
I would never be the one at the very back of the line.
All right, so everyone is good. So let's move on. Now we're going to get to some puzzles here using our combinations. So we're going to put together all of our stuff and try to figure these out. So we have a grid here, right? You're starting at point A. You're going to go to you're starting at point A and you want to go to point B. And you can only move on the lines. So you have to stay on the line, right? And you can only move up or you can only go right. So we're looking for how many different ways we have to go from A to B. So you see this red line here is one example. We can go up, right, right, and then up again. All right, so let's first look at the problem here. So what do we know we have to do each time? Right, because when we're doing combinations, we got to know how many things we're counting, right? So how do we decide what we're counting for this problem? You guys got any ideas? Remember, it's still okay if you guys are wrong.
Well, I'm guessing it's like this. The logic of this is that if we do 2 factorial, if we do like blank factorial, we're probably gonna overcount a few copies.
Yeah, so what are you going to count? Let's worry about that first. We can remember, you really, when we're doing these problems, we want to first figure out how many things are we going to count, how are we going to count them, and then we have to worry about if we're over counting them, we get rid of that.
I am thinking like 1, 2, 3, 4, 5, 6.
If this helps, I'll draw another little path for you guys. I'll draw it in blue so it's easier to see.
It's 7. It's 7 factorial.
All right, so how do you get 7 factorial?
Because if you do any way of writing this, it's always 7. That's what I'm guessing.
7 what? Like the 7 moves?
Yeah, it's always 7 moves.
Yeah, you're right. Because look, think no matter what we do, we have to move up 3 spaces. We have to move right 4 spaces, right?
Yeah.
All right, so everyone, does that make sense? So that's where we get our 7. So that's a start. We know we're going to count 7 things.
So 7 factorial, but we're probably going to repeat something.
Well, let's think about this. We have 7 factorial. That's not necessarily true, right? Because 7 factorial means it could choose right 7 times, and we can't do that.
Oh, so we have to keep it with restrictions.
Here's where the restriction kicks in, right? We can only move up 3 times. We can only move right 4 times. So anyone have any ideas for how to get around that?
It's the first time I have no idea.
Anyone got any guesses? Let's see.
Wait a minute. Oh yeah, never mind.
Okay, let's think about it a different way. What if we number our moves, right? So every right is R, every up is a U. So what would our list of 7 look like?
R, R, or it could be R. Or
Yeah,
it
so
could
we just need to arrange.
be U.
Yeah, so there's that's a pretty good thing, right? All we have to do is count the R's and U's. So how many R's do we have in total?
28.
Oh no, like just looking from, let's just say one path. In
4
one of
rights.
these paths, how many R's do we have? Like how many times do we
4
move?
rights.
Yeah, you have R, 4 R's, right? Let me draw those out. Okay, now how many ups do we have?
3 right ups.
We have 3 ups, right? U. Okay, so there we go. There's our list, right? We're counting these. So as long as we count these and we put them in order, we get our answer, right?
Mm-hmm.
So now we simplified this to from a pretty like complicated grid problem to just rearranging this row of letters.
That could be real. We could like go to every letter and we could rearrange. We could like show all its possibilities.
What do you mean by like all this possible for each one?
Like let's not worry about the rest. Let's just worry about the first 2 letters. We could do R-U-U-R. There's only 2 possibilities. And then we could continue doing that with the next one because there's only 2 like choices. So then the second one is RU or UR. And then we just have to add it together, which is another 2. And then we continue doing that.
It's a pretty good guess, but that's not quite what we're gonna do. Right? We can think about that. What method you're thinking about is literally going path by path, right? You go this way, then you go this way, or you go that way. And from there we branch on. So you're thinking in branches, but we've simplified the problem to just solving for ours. Your method will work, but let's stick to this one for now. We'll go do that one once we have more time. So remember, we just have to arrange this list of 7 letters. 4 of them are R's, 3 of them are U's. So
that probably means we have 7 choices.
Not 7.
Like 7 paths.
You have more than 7 paths. Way more than 7 paths. So let's think about how to tackle this problem. So first of all, we can't just do 7 factorial, right? Why would 7 factorial not work for this?
Because you could also do R.
Yeah, well, the 7 factorial means that they're all different, right? But we have 4 of them the same. So do you remember any problems we did earlier that are similar to this?
Probably the one where the one that says each are the one that says the president, the vice president, and the treasurer, and the one that says they're all community helpers.
Exactly. This is the problem that we're looking at here, right? This is pretty good.
But so does that mean it's the equation is 10 factorial divided by 3 factorial, and then 10 minus 7 factorial. So it's
that's for this problem. Let's think about our grid problem in terms of this. So this is the equivalent of what? We have 7 people in a class.
Okay.
And let's say we need to pick a group of 4 for one committee and a group of 3 for another committee.
So that means 7. Oh, I see where you're going now.
Yep. All right, let's go back to.
So now we're going to do 7 factorial divided by 4 factorial. And then 7 factorial divided by 4 factorial, and then 7. I mean, no, never mind. 3 factorial.
There you go. You got it. That's the
answer.
And
the same thing with the other one. This is 7 factorial divided by 3 factorial, and then 4 factorial.
Oh, you don't need to do that. This one covers all of it.
What?
Oh, well, you can think about it, right? We have 7 factorial.
Oh yeah, true.
We already got counting this, that's for the 3, we count this for the 4.
Okay.
So does everyone understand how he got there? That was a pretty complicated problem here, and I let you guys pretty much figure it out on your own. So any questions right now, please ask them in chat or unmute. You can. Has everyone else got this? All right, so now that we know how to do this problem, let's move on to similar one, but with a new restriction.
Okay, so what's the answer?
Oh, it's just the one we had over there, 7 factorial divided by 4 factorial times 3 factorial.
Oh, that's all?
The
So how many packs are there?
That is something we can leave to the calculator.
Oh.
You don't have to use the graphing calculator, just using this. Oh. Yeah, 140.
140 ways?
Yeah, there's a lot of ways. All right, so let's move on to this one. This is the same type of problem, but there is a new restriction. Every single time you go from point A to point C, you have to pass through B. Oh, yeah, you have to pass through B. I'm going to put a star here. So does that make sense? So let's think about how you can tackle this problem.
Wait, right now I'm just guessing we have to do at least, wait, 1, 2, 3, 4, 5, 6, 7, 11 moves. You have to do 11 moves to cross through B and to get through C. So I'm guessing if one example would be, I'm very bad at drawing on the computer, that.
Yeah, that works. That's one example, right? So you move right 7 times, you move up.
So
if
that means,
yeah.
I don't get it. Wait, actually I get it. So it's 11 factorial, and we can only, if we use 11 factorial, it could go 11 right, when it can only go 11 ups. It can only go
Yes, you have to correct for the overcounting, right? So how can you correct for that overcounting?
So does it mean it is 11 factorial divided by 7 factorial, and then
you're on the right track, right? We're
3 factorial.
Yeah, so that's how you would do it if it was just moving from point A to point C. But remember,
I see. We gotta pass B.
Yeah, so let's think about breaking this problem down even further, or trying to look at it from a different angle. How do we make sure we always go to B? Do you think you can split the problem up into easier bits here?
We could chop up some pieces.
Yeah, you can chop it up to pieces. So how can we do that?
I'm guessing I'm guessing we should start off with an easier problem. Maybe. Only
make the grid smaller. That would help here.
Maybe only these pieces.
Here, let me go make a smaller grid. Kimi, can you put, yeah, there you go. Clear that.
Why is there a few stars?
Oh, let me get rid of that. There you go. Oh. I'm gonna draw a smaller grid here so we can visualize that.
You should just copy and paste it.
I'll just copy and paste this little grid here. Yeah.
Yeah. I don't know if it works on Jamboard though.
Oh, look at that, it works.
Yep, it does. Oh.
Nice. Okay, so let's start again. So let's say this time we're going from A is down here. We're going to C. We have to pass through B. Same problem. But this time, let's think about breaking this down. How can we split this problem up? Because that's actually
Oh,
very
I
clear to
see what
tackle.
you mean now.
Anyone else have see this? Anyone have any ideas here?
But I have no idea. I just know what you mean now.
Yeah, so we can think about this as going from A to B first and then going from B to C. Do you think that's a valid way to solve the problem?
Yeah, we could. Actually, I'm thinking if we start on B and then go to C. And then we could start from A to go to B, all the possible ways of going to B.
Exactly. So that's how we can split the problem, right? Does everyone else see this? So now let's go back to the bigger problem.
I see now it's just a little version of this huge one.
Oh yeah, Elizabeth, yeah, no problem. You can go on, head off.
Wait, class is over?
Oh no, she has something else to do right now.
Okay.
But yeah, so Kimi, you're right about splitting this down. So now let's finish off this problem. We just have to view it as going first from point A to point B, and we can add all those to the number of ways you can go from point B to point C. Does that make sense?
Mm-hmm.
All right, everyone. So now we've broken the problem down. Let's try to solve this.
Wait, can we break it down to two pieces? A to B, like I'm guessing we should break it down to like this 3 by 4, and then B to C as this 3 by 4, and then minus these two extra squares.
Oh, Kimi, there's a simpler way. You don't even have to do that. You can just go directly from A, only going to B, and then only worry about going from B directly to C. You only have to worry about these two. So it's essentially like you're counting a 2 by 3 grid and then the 2 by 4 grid. You're adding your results up because that's exactly what this problem is.
Wait, 2 by 3 and then a 2 by 4?
So A to B is a 2 by 3, right? This is 2 here.
Oh, yeah.
This is 3. And then B to C is a 2 by 4 grid.
I see them really clearly now. Wait, but I'm just thinking, could we go... We wouldn't cross C. We wouldn't cross B. I never said we can't go down.
Oh, yeah, sorry. I forgot to mention that. Yeah, we're still sticking to only going up and right. Yeah. If we can go left and right, then you can...
Wait, but we could still not pass B like that.
Well, yeah, but that's why we're splitting up, remember? We're trying to go to B first, and we go directly from B to C. All right, so can you guys try to solve this one?
No.
Ah. All right, anyone else have an idea of how to solve
this? I
this?
literally have no possible idea.
Well, we've already broken the problem down, right? So let's figure this out. How many ways do we have to go from A to B? Let's count in the U and R again. So let's only do A and B for now. Ignore the rest of the problem. So we have 3 rights, right? So it's R, R, R. We have 2 ups. U, U. Count those. What do we get?
5 factorial.
Divided by?
Divided by 3 factorial and 2 factorial.
Okay, so now we've gotten to B. We figured out all the possible ways to go to B.
Then the number to B to C is 8 factorial, and then 2 factorial, and then 4 factorial. Wait, no.
Almost. You double check your counting here real quick.
No, 6 factorial. 2 factorial and 3 factorial.
Oh, sorry, what?
2 factorial and then 3 factorial, I'm thinking.
Not quite. Remember, we have the 4 here. 4 arcs.
Oh, 2 factorial and 4 factorial.
Yeah, so now let's put this problem together. We figured out all the ways we can go from A to B. We figured out all the ways we can go from B to C. Now, how do we all that together?
So I'm guessing if we do the multiplication, and then we could just add both together.
Exactly, we can just add them together, right? The methods, how we go to B does not affect how we go from B to C. So therefore, we can add both these together. So the answer is
it's basically A to B, and then C to B.
Yeah, A to B.
It's basically the same thing. It's basically like if we miniature the grid, it could be A to B, this be A to B, and then we could do the same exact same moves. It would be B to C. So does that mean these two, we could just add them together? 11 factorial divided by 5 factorial.
Oh, no,
And
no, remember, we can't add them together. If we add 11 factorial in that, we were assuming that we can also go to this point here and this point here and all these that are not B.
oh, so how are we supposed to do that? Could
Oh,
we
remember,
double it? Could we double it like fractions?
oh no, Kimi, we already solved the problem, remember? So we figured out, think about it,
Oh,
if we know all the ways we can go from A to B, then we just find all the ways to go from B to C. We add these up and we have our answer, right? Because we don't have to worry about going to these or going to these, because we will never touch these parts.
we could. We would touch these parts.
You
Look.
see all those little dots here, like this one, this one, this one. These we will never go to.
Oh, I see.
Because if we go to any of these points, that means we'll never be able to reach B.
Unless we cheat.
Well, yeah, but let's try not to cheat
Like
when we're
that.
solving. Alrighty, so let's go to our final problem. We have 6 minutes left. This one might look pretty complicated, but remember, try to break it down to something simple. So,
Oh, I think I've done this before. So do we just do the exact same thing, but we subtract it from the grid in the very middle. And we put the grid from at the very middle as one big square.
not quite. So, we explain the problems first, everyone. So we're trying to go from point A to point B, but this time we have one rule, which is we cannot touch this middle point here. So normally,
Wait, does that mean we can go down?
oh no, you can still go up and right.
That is just unfair.
Well, you still have the same amount of methods to go through, right? You can go this way. That still works. You can go like this. Still works. So there's still many ways to get there. It's just you can't use that point there in blue. So how can we solve this problem?
And now I'm just trying to mark out every possible way of doing this.
You can do that. Just take you a while.
2 hours.
Okay, but Kimi, let's wait to solve this problem first. So you might not have time to do a full thing.
I did it.
But please think of the logic of how to do that.
I did it. The basic way of doing this is that this part is there are 8 ways to cross this part.
Well, think about it now. If we find every single path that goes from A to that point and we subtract it from our total, isn't that like it's never going there?
What do you mean?
Well, we want to make sure that we never go to this point, right?
Well, we could go to the middle. We could go around it, right?
You're allowed to go around it. That's the point of the problem. So we can just subtract all of the lines where we go to this point. So you can calculate normally. Let's pretend we're just going to calculate points going from A to B. And then we just minus all the things. Let's call this point X. Minus all the things where you're going from A to X. All right. And then as well as minus going from B to X. You just need to subtract we have to subtract all of the paths that we take that go through that point that we don't want to go through.
Well, now we can.
I just added the grid back. Yeah, let's pretend the grid still is not there. So does that make sense for anyone?
Poof. It disappeared. Well, this is so complicated.
Yeah, these are some pretty tough problems. So yeah, it's okay if you don't completely understand them, but if you have any questions, still try to ask them and I'll try my best to explain them to you. So do you guys understand how we're trying to break this problem first?
My question is, can we cheat and go through the point?
Well, if you go through the point, this problem wouldn't be really useful, right? It's just the same as the problem over here.
Yeah. And then there will be more than 140 moves.
Oh yeah, much more because we have a bigger grid, right?
And then if we expand it to 100 by 100, there'll be like more than 1 million ways.
All right, so
Explain it. I have no idea what to do.
yeah, so we just have to get rid of the points where we go through X. So if you have any possible path where we go
Wait. Does that mean?
through X, we cannot use those.
So does that mean if we cross this line or this line or up here and then to the side or from up here? Oh wait, never mind. Okay, or from down here and then up there. So basically, we can't touch these 4 grids.
Oh, no, you can touch those 4 grids. Why
No,
can't?
I don't mean like the sides. I mean like the middle of these 4 grids. We can't touch like the inside of these 4 grids.
Oh yeah, because the inside you only have 1 point, right? So we can't go there.
Yeah, duh.
No, but again, do you understand why we're trying to subtract all the points where we go through the middle here?
Yeah.
So how can we subtract those points? Where would the combinations be? You don't have to solve the problem. Just explain to me where we're counting from. Because that's the most important part.
This.
Oh, we're
What
trying
is half of 90? What is half of 90?
45?
This is a 45-degree angle.
Well, yeah, but we're gonna pretend we can't go through process. So we have to count, we have to get rid of the lines from A to X here, right? And then from X to B.
Yeah, but that's gonna take like 2 years.
Well, no, do we know how to calculate all the possible paths where you go through X? Do you still remember that? It's this problem, right? The problem we did earlier.
Yeah, exactly. But like, I feel like we should just get the answer to a normal problem, and then like there's a few ways that you could go through X, like that way, up and then right, side and then right, and then from this way. Oh, you can't go that way. So there's only
Okay,
there's
well,
only 3 ways.
so guys, let me explain to this real quick so you guys can understand this problem, and then we'll head off. I don't want to keep you guys for too long after the meeting. So the basic point of this problem was to learn that we cannot go through this point in the middle. We lose a spot. So this problem is the equivalent of finding all the possible ways to go from A to B. Okay, I'm just going to write that as this. We have to find all the possible ways to go from A to B. We have to subtract all of the paths where we go through this point. So we still remember how to solve for that, right? Remember in the last problem here, oh, not background. In this problem here, we already figured out how to solve for all the possible methods when we're going through a single point, right? We go from A to B first, and we add that to all the ways to go from B to C. So this problem here, Kimi, could you erase that real quick?
Okay.
Yeah, so let's call this point X, right? We have to subtract that from all the ways where we go from A to X plus all the points from X to B. So this little bit in parentheses here, this is all the possible ways we can go through this point X. We just subtract that from all the possible ways we can go from A to B.
Which is 3.
Oh, it's not 3. So let's actually show you the math for this. So first of all, A to B, what is that? 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. So that'd be 10 factorial.
10.
Right?
X to B, which is 1, 2, 3, 4.
That's how much we have
4.
from A to B. You have to subtract that from A to X plus X to B. So A to X here, I'm gonna draw a little arrow.
Could you do the whole thing? I want to see how many moves there are. I bet you there's like 2 million.
Yeah.
I bet you there's something close to 200.
I'm gonna move this over here so I can finish drawing it. Minus all the points from going A to X. So that is.
I bet you at least 30 moves.
Plus X to B. X to B is just a 1 by 3. So again, 3 factorial.
1 by 3?
Again, you don't have to write all the factorials for these small numbers here. I'm just writing it so you can, like, it stays consistent. So what we have here in the end, let's finish up real quick. So the first bit here, 10 factorial divided by 7 factorial times 3 factorial. This is all the possible ways we can go from A to B. And then we're subtracting that from all the ways where we can go from A to B while also passing through X. So the part in parentheses here, the 6 factorial divided by 2 factorial times 4 factorial plus 3 factorial divided by 1 factorial times 2 factorial. This is all of the ways we can go from A to B while also passing through X. We have to subtract that from our total ways of going from A to B. And that's how we get our answer.
So what's the answer?
It's a big number. You can calculate this if you want, but for everyone else, sorry for holding you guys a little bit over today. Yeah, I know that was some pretty hard math, but thanks for coming. You guys are free to go. Yeah, the discussion problem will be up maybe today or tomorrow.
Could you just take like 2 minutes to calculate that?
Yeah. I just have to let everyone else go first. All right, Kimi, let's calculate this.
Okay. 10 no.
You can do this by hand, but I'm just gonna do.
Prancy bubbles.
All right. Oh wait, what? I'm on the wrong calculator.
You're in the right calculator.
There you go. We don't need the graphing calculator. We can use this one. Does this even have 10 factorial? Is that a thing? Oh, it does. Cool. Right. So it's got 10 factorial here. We're going to divide that by 7 factorial times 3 factorial. We're going to minus 6 factorial divided by 2 factorial. 4. Oh my God.
Everyone's still here.
Yeah, everyone else, you guys are free to go. You can stick around if you want to see the answer to that problem here. We're going to actually calculate it. But you guys are free to go.
I bet you it's more than 30.
Oh yeah, it's going to be more than 30 for sure.
More than 50?
Yes, I think so.
I think it's more than 100.
There you go, 102. That is your answer. So again, to reiterate,
There's 102 ways.
you can go count that out if you want, but yeah, it's all the methods.
Okay.
All right, cool. So you guys got that. We will do a quick review of all these things at the start of next class, but we're going to try to move on to some sort of more fun math problems next week.
Oh, could we do something like stacking stuff again?
Yeah, we'll try to find some cool puzzles. But that's it for today, guys. Thanks for coming to this meeting.
Thank you.
Thank you.
Hey, no problem. See you, Kimi.